All right, so let's talk about related rates.
You don't have to know.
Oh, I might. Hold on 1 second. Yes. Yes, I do.
Sorry.
Stupid Norton. It amazes me that, like, even when I put, Windows 10 has a do not disturb mode, but it still allows things to disturb you when it's on. So they haven't quite mastered that concept, but
Windows pretty much just disturbs you.
yeah, it's pretty disturbing. Yeah. All right. So here, related rates problems are they all start by describing some scenario, like something's happening where things are changing. Imagine a balloon being blown up, or there's a classic example that we'll look at where we have like a ladder that's leaning up against a wall and starts sliding down. So there are like quantities changing over time. And they'll give you information. They'll say, okay, this one quantity is changing at this rate. And can you tell me how fast this other quantity is changing? And so they're all time rates of change. So meaning we're always differentiating with respect to time. But what we want to do is kind of read the problem, try to understand conceptually what this problem is describing. Sometimes it helps to sketch, sometimes it doesn't. And then we want to make an equation that describes the relationship just between the quantities themselves. Like, for example, if they talked about a balloon being blown up, I might use the equation volume equals 4/3 pi r cubed. And if I differentiated that equation with respect to time, I would end up with an equation that described how fast the volume is changing, like dv dt, related to how fast the radius is changing, dr dt. So there's like some implicit differentiation. We are respecting time, and we're often dealing with variables that are not time in our equations. So let's begin by looking at this example where they talk about a spherical balloon being blown up. And they tell us that the volume is increasing at a constant rate of 2 cubic feet per minute. That's a rate. Right now, what we want to do, and hopefully we've been sort of slowly trying to do this over time, but really making the connection that whenever I see a rate, I need to know that's a derivative. They're telling me the value of a derivative. And then they're asking me to find another rate. They're asking me to find what's the rate at which the radius is increasing when it's 3 feet, when the radius is 3 feet. So I often start these by just organizing the information. Like, here's what I know. The rate that they give me, the rate I know, is this 2 cubic feet per minute. Look at those units. Cubic feet per minute. It's a rate, so I know it's a derivative. What is it the derivative of? With respect to time, and the derivative of what with respect to time? Volume, because cubic feet, right? Take your Q's with the units. Cubic feet per minute is volume over time. So that's a dV dt. We know that dV dt is equal to, and now its volume is increasing. That tells me that the derivative is a positive 3. If the balloon was deflating at that rate, it would be a negative derivative.
Isn't it 2 feet cubed?
Oh, yep. Ha, yep. Just, joking. Playing around. And now find the rate at which the radius is increasing. So what we want, the rate at which the radius is increasing. What derivative is that? dr dt. And we want to know what it is when the radius is 3 feet. So here's just sort of my organizing information. I'm going to kind of keep my eye on the ball. I'm not going to be able to use this value right off the bat. But if I think about this scenario, the next thing I want to do is think, well, how are volume and radius related to each other, generally? We could Google it or look in the inside cover of a textbook and remind ourselves that the volume of a sphere is 4/3 pi r cubed. So there's an equation that relates v and r together. Notice that there is nowhere to plug in dv dt, right? And nowhere no algebra I can do here to find dr dt, because those quantities are not in that. But how do I get an equation that does involve these quantities? With respect to time. Let's just differentiate this equation with respect to time. And on the left side, what do I get if I differentiate v with respect to time? We get dv dt. Yeah, we get the derivative of volume with respect to time. And then what do we get on the other side? 4 pi r. Nope. Okay, so you get that 4/3. So you get that because you're using the power rule here, right? And those 3's cancel. We're missing something.
Oh, and then DRT?
Times dRdt, yeah. We are respecting time, so like just being kind of hyper vigilant about that as we differentiate is important. I mean, hopefully if we forgot that dRdt, hopefully it wouldn't take us too long to recognize that we must have made a mistake somewhere, because it's going to be really hard to find dRdt if I don't have an equation that has dRdt in it. So, we do some simplifying. These will cancel. Also, we know that dv dt is equal to 2. So I'm going to use this information. We have 4 pi r squared dr dt. I'm going to solve and do algebra now. Solve for dr dt. I'm going to get an expression that tells me what dr dt is in relation to what its current radius is. We'll just divide by 4 pi r squared. And that tells us that dr dt is, after we reduce, 1 over pi r squared. 2 pi r squared. I can find dr dt at any value of r. They've asked us to figure out what dr dt is when the radius is 3 feet. This is a huge balloon. Yeah. So now let's do it. Let's plug in 3. So 3 squared is 9, 18. So 1 over 18 pi. There it is as an exact value. But it's an application problem, so I think it kind of makes sense to approximate. If you're doing this on the calculator, I want to think you probably would have to use parentheses around the bottom in order for it to understand that pi is a factor in the denominator and not just an overall factor. Yeah, 0.0177. What would the units be?
Meters per minute?
Close. No, it is linear units. It's just that those are feet. So look at the volume units. Feet. Yeah, just regular feet per minute. Like this was cubic feet per minute because that was a dv dt. So this is a dr dt. The units of radius in this problem are feet. And the units of time that we're working with are minutes. It inherits those time units here from that given rate of change. So this would be feet per minute. How's that? Questions on like any phase of this problem? You want to do another one?
Sure.
Sure. Okay. A lot of what's involved in solving a word problem is just kind of parsing out what they're telling you. Even without any background in physics, if we know how to read the mathematics and what they're telling us, we could still solve this problem. So they tell us that the kinetic energy, which they're calling K, measured in joules, of an object is given by K equals 1/2 mv squared. So they're giving us some equation. Little m is the mass of the object and v is its velocity. Okay, and then we have this wrecking ball with a mass of 250 kilograms. And they're telling us that it accelerates at 5 meters per second squared. And we want to know how fast is the kinetic energy changing when the velocity is 30 meters per second. So they give us an equation that relates kinetic energy to mass and velocity. One of the things I like to do when I'm doing these types of problems is just, first of all, it looks like there's 3 variables there. We have K and M and V. I just want to be aware of what's changing. Like, what are the quantities that are changing? Are there any quantities in this equation that are static in this scenario? The mass. The mass is not changing. So if there's any quantity that is not changing over time, you can plug that in right away. Any quantity that does change over time, you have to wait until after you differentiate to plug it in. So we can plug in the mass of 250 kilograms. So we get 125 v squared. So now we've boiled this down to an equation that relates 2 quantities, kinetic energy and velocity. In a related rates problem, they're always going to do 2 things. They're always going to tell you the rate at which one of those quantities is changing. And then they're going to ask you to find the rate at which something else is changing. So there's a know and there's a want. What is the rate that they gave us? Say that again?
5 meters per second squared.
5 meters per second squared. What is that the rate of change of? Well, it is acceleration, which is the rate of change of velocity, right? This 5 meters per second squared is 5 meters per second per second. That's a v over time. So in fact, they told us dv dt. What is it that they are asking us to find? How fast is kinetic energy changing? dk dt, and when are we interested in that value? Yeah. We have an equation already that involves the quantities, that relates the quantities K and V together. We wish to have an equation that relates the quantities, dv dt and dk dt together. How do we get that equation? Yeah, let's differentiate with respect to time. And if we differentiate this equation with respect to time, what's the equation that we get? dk dt on the left.
250 v times dv.
Yeah. I'm going to stop there for a moment and see if there are questions about how we figured out this know and want and how we got to this equation. With this information they gave us, it's not like they weren't exactly hiding the dv dt, but we had to just remember, acceleration is the derivative of velocity. We did need to recognize that when they told us acceleration, they were actually giving us the value of dv dt. Do we have enough information now to find dk dt when v is equal to 30? Yeah. So dv dt, this is equal to 5. So I'm just going to plug that in first. 5 times 250 is equal to 1250. So now I've got dk dt as a function of v, and let's just plug in v equals 30. 37,500. So we have a numerical result here. What are the units? What is it? Joules per second, yeah, because it's going to be units of K, which they already told us were joules in the opening sentence of the problem, over units of time, and those time units are inherited by the units that they've been using in the other rates they gave us. So joules per second. Fun? I love these problems. Because the reason I love them is because, like, I've been doing them so long, but, like, I know there's a pattern, right? I know they're always going to tell me a rate, so I'm, like, hunting for it. I'm on the hunt for, like, I know they're going to give me a rate somewhere. Sometimes it's couched in language of acceleration, and I need to understand that that's a rate of change of velocity. And then, and then there's going to be some rate they give us. There's like a clear pattern as to, like, the kind of information they give you and what they're asking you for. There's going to be other word problems we see later this chapter when we're doing these like optimization problems. But they read very differently, right? So they're like different word problems, but we can kind of understand we can kind of recognize what type of problem we're doing based on the kind of information they give us and what they're asking us to find. So let's do one more. This example probably appears in every calculus textbook that has ever been published. All right. So we have a ladder slipping down along a vertical wall. If the only understanding you had of a culture was reading calculus textbooks, you would think that there is a rash problem of, like, ladders slipping down walls. All right, like, it just happens all the time. But let's go ahead and just, have fun with this problem. The ladder is 10 feet long. We'll assume that it's a fixed length ladder, right? So it's not going to collapse or anything. And it's leaning up against a wall. So I'm going to just draw this. There's the wall and the ground. And then here's the ladder. Probably should be not quite so steep. Here's our ladder, 10 feet. That's fixed, right? The length of the ladder is not changing, and so I know that whatever equation I come up with, I get to use that as I could put the 10-foot length in there right away. But as this ladder is slipping down the wall, some things are changing. Right, so the top of it is slipping down at 10 feet per second. And as the top moves down, of course, the bottom is sort of kicking out from the edge of the wall. So we have these other quantities at play, like, I don't know, maybe this length here we could call y. This length along the bottom we could call x. So, all right, this is a related rates problem. I know somewhere they've given us a rate of change, right? And they're going to ask us to find another rate of change. So what is our no? Like, what is the rate they gave us? 10 feet per second. What is equal to 10 feet per second? What? dy dt. And let me ask you a question. Is y increasing or decreasing? So what does that mean about its derivative? Negative. So dy dt is negative 10. Now, before we do actually, let's go ahead and do the one first. What is it that we want? We want dx dt.
When x equals 6.
Yep. Great. So, so we want to know the dx dt, the rate at which that is increasing or increasing, obviously, right? It's pushing out from the wall. If it's pushing out from the wall and x is getting longer, right? X is increasing. What do we expect to be true when we find dx dt?
It's 2 positive.
going to be positive, right? And the fact that we set it up so that dy dt is negative, like that should bake into this problem that we're going to get a positive result when we find dx dt. All right, we've organized our information. We kind of know what's going on with this problem. We need an equation that relates x and y together. Yeah, let's use Pythagoras. So that looks like x squared plus y squared equals 10 squared. So there's an equation that involves x and y. How do I get the equation that involves dy dt and dx dt? Yeah, differentiate with respect to time. Like that's what we're always going to do with these related rates problems. We get the equation that involves just the straight up quantities they're talking about, and we get the equation that involves the derivatives in this problem just by differentiating the equation.
But we want to set this up in the terms of dy dt, right? So that we can.
Well, if we just differentiate now, we'll just have an equation that has these derivatives involved, and we can plug some known quantities in and do some algebra. I have seen some people approach this problem by first solving the equation for x or solving the equation for y, doing some algebra first, and then there's like a square root involved, and like that's okay, and you can get the right answer. It's probably, I think, less algebra to differentiate right off the bat rather than solve it for one of the variables. If we differentiate with respect to time, what do we get? What's the resulting equation?
2x dx dt plus 2y dy dt equals 0.
Mm-hmm. Why 0?
Because even though we're doing a power, it's still a constant.
Yeah, 10 squared is a constant. So its derivative is 0. We know the value of dy dt. It's negative 10. I'm just going to plug that in. So we have 2x dx dt is equal to, minus 20y is equal to 0. And now we could do some algebra, solve this for dx dt. Divide both sides by 2x and do some reducing, and we find that dx dt is equal to 10y over x. Now we're being asked to find what is dx dt when x is 6. So I look at this equation, I'm like, great, I can plug in x equals 6, but I kind of hit a wall. Pun intended. What do I do? Like, what am I missing? Why? So we want to be able to figure out what y is when x is 6. Do we have a path forward there?
Yes.
Yes. What is it?
Substitute 6 for x
Where?
in the denominator.
We multiply.
Well, right here, you mean?
Yeah.
Yeah, but we want to find dx dt when x is equal to 6. So we can substitute x equals 6. You're absolutely right. But I would still have two unknowns. Right? I'd have a hard time finding either dx dt or y if I substitute x for 6 in that equation. Maybe in the original equation, right? This relates x and y together. So I could find y when x is 6 using the original equation, and then I could plug both those values in here. So y squared is, let's see, 100 minus 36 is 64. So y is 8. Yeah. All right. So now we're just about done. So when x is equal to 6, we have 10 times 8 over 6. You could do some reducing. 3, 4, so 40 thirds, which we could also approximate. .33. What are the units?
Feet per second.
Feet per second.